Hello everyone, welcome to lecture 14. From this lecture we're going to talk about the electromagnetisms. In chapter 10 mostly we'll talk about the governing equation and the constitutive laws of the electromagnetisms. In this lecture we'll cover the section 10.1 to 10.5. Mostly we'll talk about the some laws of the electromagnetisms, and in the last section 10.5 we'll talk about the some electromagnetic properties of the medium. This chapter actually reviews the element concept of the electromagnetism very briefly, so for more details please refer to the introduction to electrodynamics, the textbook about the electrodynamics by Krebs DJ or some other books. So please recall the some knowledges that you learned from the general physics in college. Electrical charges quantized to proton and electron, and elemental electrical charge is the one electron, and one electron has this much of the electrical charge, and the volume charge density is rho v and surface charge density is rho s. So volume charge density means the inside a certain volume, how many charges in there, and if the surface charge density is for a certain area, how many charges are in the on the surface. And this charge is constant because the electric charges cannot be created or destroyed. So the electrons or the protons cannot be destroyed or created. So charge conservation means that if you have a certain isolated system like this, there's no change in net charge. If a body of volume is enclosed within a surface, the total current across the surface must be equal to the change in the free charge enclosed. So from the charge conservation, the continuity equation is stated in terms of the current density, and the surface integral of J and ds is the time-varying charge enclosed in the system. Or you can say that the d over dt and the volumetric integral of the rho v dv. So, and recalling the divergence theorem, the surface integration can be converted to the volumetric integration, and here this one becomes the volumetric integration, and so then you have only the d rho v over dt. So the current density, or the divergence of the current density, is equal to what the volumetric charge density, the change in volumetric charge density with respect to the time. The electricity and the magnetism associated with the static and moving charges, it causes the electric field intensity E and magnetic induction B. So it means that if you have some like moving charges with some velocity, then it creates the current and the electric field E, and at the same time it creates the some kind of magnetic force called magnetic induction. So they are all associated together. These are the mathematical theorem that we use in the electromagnetic or electrodynamic theory: divergence theorem, Stokes theorem, and their operator. I think this will, for more details, you can look up the vector calculus. Let's talk about some terminology. Conduction is the mobility of the free charge. So it's the electron moves, then it's called a conduction. And the property that quantifies the conduction is called the electrical conductivity of a material. And it shows the availability of the mobility of the free charge of a certain material. And mobility creating a current of free charge, and using this electrical conductivity in geophysics, people used the electrical resistivity survey and resistivity Coulomb. And polarization is expressed or described the permittivity of medium, epsilon or kappa. And permittivity describes the ability of the medium to become polarized in response to electrical field. So if you have, for example, like water with some ion, like sodium and chloride, and if you put the electrical field plus and minus here, then the sodium will move to the negative pole and the negative electrode or node, and the chloride will move to the cathode. This is called polarization. And it's a moving charges, so it's more about the conduction. But if this sodium and the chloride ions are bound, they are not free to move, then the the local mobility of the plus minus charges in the electric field, it's called it creates the local concentrated ions, or the local polarity, and that ability is described with this permittivity. And for that, the GPR, using that concept of GPR is used. Magnetic permeability is the ability of the medium to become magnetized in response to a magnetic field. And charge movement creates a magnetic field which magnetizes the medium. And using this magnetic permeability, we deploy the electromagnetic method and magnetic survey to detect some magnetized minerals. We can categorize the 6 fields. One is the Tae-Hyuk column is the electrical field, like electrical force, and this is magnetic force related one. So D is electric displacement. It's about the displacement of like actual charge, and P is polarization, and it's combined with the electrical field is expressed. And H is the magnetic field intensity, and M is the magnetization of a material, and together combined magnetic induction is expressed. So let's talk about the static charge in a free space. It means that the charge is not moving. So electrical force, electrostatic force between two charges, Q1 and Q2, by a distance r. In a free space, F12 is expressed with the Q1 and Q2 and the distance, the r square. And here the E12 is the electrical field, and so E12 is the electrical field applied to Q1 generated by Q2. And if you just multiply the Q1, then it becomes the force that's applied to the this Q1. And here, epsilon naught is called the permittivity of free space, so like a vacuum space, and that's the constant number. Here, using the Coulomb's law, this is the force between 2 point charges, and we can always apply the superposition rule, and sum of forces generated by all other charges. Then force exerted on a point charge Q by a charged object with homogeneous volume charge density rho v can be expressed with some volumetric integral like this. So if some material here has the charge density of the rho v, then each charge will act the Coulombian force like this, and if we integral everything, then this is the final, the force, the total sum of the force that's exerted by the this charged object. Then electrical field is defined as the force exerted on a positive test charge when its charge goes to 0. So then from the Coulomb's law, the electrostatic field around the point charge is like this. So then if you have, you can calculate the E that's exerted by this the Q, the charge Q, point charge. Static charge Q placed in an external electrical field E, EXT experience a force F parallel to the field. So for example, if you have cathode and the anode with the electrical field E, then the charge here, the Q, will feel some F, and that F is Q times the electrical field EXT. Consider, so this is the continuation. So from there, we're gonna derive and see how how the Gaussian law is derived. Consider a body with the charge Q surrounded by a convex surface. If the enclosed body is electrically neutral, then the enclosed charge Q is 0. One can move a test charge along the enclosing surface and measure the electrostatic field at every point. The integral of the electrostatic field emanating normally across the surface is equal to the enclosed charge Q. If the volume enclosed consists of spatially distributed charges with volumetric charge density rho v, then the enclosed charge Q is the volumetric integral of the rho v. So the Gaussian law, the Q is the volumetric integral of the rho v, and that's the surface integration of the test charge, like all over the surface of the volume. So we can derive the external electric field outside the ball of the radius r in which the charges are evenly distributed. So if we have some kind of a ball, and inside is the charges are evenly distributed, so it will have the charge density of the rho v. Then for a Gaussian surface, epsilon surface integral of the E times ds is the Q int, so that's like this one, enclosed the charge Q. Then here the enclosed charge Q, the capital Q is the same with the Q, the small q, and E is the symmetry because it's a ball, like a sphere, and direction of the electric field is the same with the surface, the normal to the surface. So then it becomes, you can take out the vector E with the absolute value outside of the integration, then and S becomes also the scalar value, and later then this term is just a surface integral of a ball. So if it's a sphere with the radius r, it could be r, then you can multiply 4 times pi r square. So then this is the Q, and epsilon time this becomes the Q. So, or the electric field is 1 over 4 pi epsilon naught times Q over r squared times the normal vector. And here the electric field does not change with Q is when Q is concentrated anywhere in the ball. So electric field, that means that the inside, whether you have all the charges here or whether charges are evenly distributed, electric field applied at the same distance will be the same. Okay, so then using this kind of a concept, we can also describe and define the potential V. The electrostatic potential V is defined as the work required to bring a positive unit charge from infinite to a point A in the vicinity of the charged body. So let's say you have a Q here, and at R is infinite, we are bringing it to a certain point here, to A. Test charge. And it's called the potential. So as the voltage and the potential have the same unit, and they share the same concept. So if you have a high voltage, it means there's a high potential. So then it requires higher work or the greater work to bring a positive charge to the point. Here the I is the path. So this is the I, or the L, you can say the L maybe. And negative sign is the sign convention. Here the electrical field is force divided by Q, so it's Newton over Coulomb. And V, the potential, is what? Electrical field times the length that the U worked. So Newton times meter over Coulomb. And this is the voltage V, or the work, the Joule over Coulomb. Electric potential around the point charge is like using this equation, and we derived this one before, right? So here, and you get this equation. And assuming a closed path or loop, total work should be 0. So that means that if you have a point test charge here, if you just move the charge with a closed loop, then the total work that you've done will be 0. Well, even though it's like this much of the work, then still it's gonna be the 0. Because the potential is defined as the line integral of the electric field at a point can be written in terms of the gradient of the potential V, and that's given here. And you can expand to get this kind of a relation, and it's called the Poisson's equation. And then now that we can consider a charge that's moving at a constant velocity V. So it's like a charge moving in a electric wire, like current. So current is actually the charge density that's moving constant V. And because it's moving, magnetic induction is generated. So the magnetic induction B that each charge Q creates at a point, at a position R, here the position R here, is defined as, it can be calculated like this: mu naught over 4 pi times Q and velocity V, and the normal vector divided by the R square. So if you think about the electric field equation, it's pretty much the same. This difference is that you get the velocity term multiplied. And it's a Biot-Savart equation. And here the mu naught is the magnetic permeability of free space. Cross product indicates that the direction of the force P is perpendicular to both the direction of the movement V and the unit length vector n. So actually here it could be this direction either, or it could be this direction. A moving charge generates a magnetic induction field, and it interacts with the external applied field, the B. Thus the resulting force F is expressed like this. So before it was just like for the electrical field, Q times the field, and here magnetic induction times V times Q. The difference between the Gaussian law of the magnetism and Gaussian law of electricity is in the electricity, positive and negative charge can exist alone. So you can think of proton or you can think of electron existing alone. But the magnetic poles cannot. So integral over magnetic flux across the Gaussian surface is always 0. But it's not in the electricity. Here, this slide shows finally derives the Ampere's law. So then the magnetic induction, the line integral of the magnetic induction is the same, equal to mu times the current I. So if you have I, where the charge is moving at a constant velocity, then it creates the magnetic induction B, like a magnetic field. And this field has correlation with this magnetic, the current I. Instead of a conductor consider body with a current density J, then instead of mu naught I, so you can replace the I with the surface integral of the current density J times ds. Then this will be the equation for that. So time varying field. So there are three possibilities where the charge is not moving, or the charge is moving at a constant velocity. The last one is the charge is moving with some acceleration. So it's like the fields are varying, magnetic fields are varying with time. Then we can still use the all different laws here. This is the Coulomb's law and Faraday's law, and Maxwell's law, and together, and it's Ampere and Maxwell law. So here, this term is about the charge density J, the flux, under the current density, times mu is like a Ampere's law, it's like the I, right? And it generates the magnetic force. And here, an electrical field, or the electrical field changing time creates the magnetic field. And together, it becomes the magnetic induction, B. Lastly, now we'll think about these properties or the behavior as a material property. So if you have the electrical field that's changing over time, like plus is here for a certain like short amount of time, like 1 second, and then it becomes minus, plus minus. You can think of like alternating current like this, or alternating electrical field. Then if this is the free space, then there's nothing to be polarized, or there's nothing that can move because of this electrical field. If you have some point charge, and this will go here and here and oscillate back and forth in marching with the field, time varying field. And what if you have some material like clay? Clay has negative charges on the surface, and then if the current is moving, then this minus charge will be here, and then will be here, so it will locally concentrate it, but in march with, in harmony with the electrical field, external electrical field, and that's it's called a polarization. And when there is some polarized current, or when there is some time varying current, and it creates the magnetic field. So it as the polarization vector P and the magnetization vector M, because of the inclusion that you're putting inside the electrical field here. when a dielectric material is placed within an electric field, positive and negative bound charges move locally. Therefore, a net charge appears on the surface of the dielectric. One side has a positive net charge and the other side a negative net charge. Then it's called this dielectric material has become polarized. So if this is the dielectric material, then the negative charge will be concentrated here and positive charge will be concentrated here, and then you get the polarization vector P in this direction, and the material is now polarized. And you can think this E is changing every day like this, like with the sinusoidal function, like plus minus with some frequency f, then this polarization will changing with this electrical external electrical field. The effect of polarization can be modeled by replacing the polarized dielectric with surface and volume charge distribution. And given a Gaussian surface within the dielectric, if you have the volumetric charge density which is bounded, then this will give the polarization. And you can also sum up the free charges and the bounded charges, because they both contribute to electric field intensity. So this is the field intensity, and surface charge or the volume charge of freely moving and the bounded one contributes to the electric field intensity. So then this equation here, this part is P, right? So rho P ds. So then inside this integration, the area integration becomes the epsilon naught times E plus P, and this will be the whole electric displacement D. Then polarization of the bound P is linearly dependent on the intensity of the applied electrical field E, and the vector E and P are parallel, so that the P is psi times epsilon naught times E. So then this D is initially epsilon times E plus P and epsilon times E plus psi epsilon naught E. So then we can take out this and this one, and this will be penetroside inside the penetroside, so that the permittivity of the medium epsilon is 1 plus psi times the epsilon naught. And here epsilon naught is the electrical permittivity of free space, so without anything, like a vacuum. So then what's added here? So the added one is this electric susceptibility, psi. And depending on the material, this psi value is different. Like the water will have like 80, and like vacuum has 0, and maybe like alcohol have some value, like, and oil have the other value too. And likewise, we can also think about the magnetic induction, the B. And similarly, using the similar approach, the magnetic field intensity H is the magnetic induction minus the magnetic permeability of the material. So this is the M part is a movement of the bound charge, and that's contributed by the material magnetism. And B is the together the free and the bound charge, and the H is the movement of the free charge. It's like a electric field, the electric field intensity. So then you can see that the magnetic induction B is expands to mu times 1 plus psi m times H, and here, and this becomes the material property. And here the mu naught is the magnetic permeability of the vacuum or free space. And lastly, the third constitutive equation is Ohm's law. This relates the current density J to the electric field E, and J equal to sigma times E, and here sigma is electric conductivity of the material. So it's a material property. Okay, this is the end of lecture 14.